Right. Once you got into this, this actually wasn't a very difficult question. You've just got to read all the information and use it correctly. So it tells us this is the I direction, J direction is the direction O to E, and then the K direction is the direction O to C. Now from that, and I don't even know if you need all these, you can write the position vectors of all the points just by looking at the diagram. I don't know, F, G, oh, I've got a little bit close together here, because O to A is just going to be 3I, because that's just 3 in the I direction. O to B then is going to be along O to A, and then we're going to go in the K direction, and if you look at the diagram, we're going to go 0.8 meters up. O to C, 0.8 K, because that was the direction the K direction was. O to D, we're now going to go along the side and then up. So along the side is J direction, up is K direction. O to E is just 1.2 J. Just going to move some of these. No, can't separate these out. Hold on. There we go. O to F, so you go along to A and then back to F. Okay, and O to G, well, we go along to F and then up. And now I've got absolutely everything I could possibly need to know about this shelter. So I've used this information. It wants an equation of the plane BCDG, so that's the kind of the slopey roof bit there. And it wants it in the form using a normal vector. So I want to find a normal to this plane. So to find a normal to the plane, I'm going to need two different vectors that are on the plane, and then I can find out another vector that's normal to both of them. So on my diagram, we want C to B. So C to B, you can work it out using all the vectors, but obviously that's the same as O to A, which is 3I. And then I could use C to D, because that's in a different direction. So OD take away OC. And if you do that, I'll get those two. So now I've got two different vectors that are on my plane, and I want a normal to both of them. Okay, so if I call my normal vector A, B, C, for example, then I want to find one such that CB dot n equals 0, because I want the perpendicular, and CD n equals 0. So CB, conveniently, is 300. Okay, so I can see that 3A has got to be 0, so A is going to be 0. CD then is 0, 1.2, 0.7. So from this, I get that 1.2b plus 0.7c is going to be 0. Now remember, for the normal, I just want any vector that is perpendicular to both the other two. And there's going to be an infinite number of answers because they're all going to be scalar multiples of each other. So I'm just going to say what happens if B is 1. If B is 1, then I get C is negative 12 over 7. So that means a possible normal vector is 0, 1, negative 12 over 7. But that's got a pretty horrible fraction in there. So I could scale that up by multiplying everything by 7, so I can get 0, 7, negative 12, which is just a little bit nicer to work with. Just going to move this part of the question out of the way for a minute. Right, so now I've got a normal vector, so I know it's going to be r dot 0, 7, negative 12 equals d. Now how do I get the d? Remember, d is a dot n, where A is any point on the line. So, on the plane, sorry. So I'm just going to pick a point on the plane. For example, we could pick C. C is on the plane. So O to C was 0, 0, 0.8. Okay, so my equation is going to be r dot 07 equals, so let's see what D is going to be. It's going to be 0, 0, 0.8 with my vector, which is 0, 7, negative 12, which is negative 9.6. So this is now my equation of my plane. Okay, now we can look at the second bit. So it's going to support the roof. One of the poles is attached to the ground at the centre of OAEF and the other point to the roof. And we want the shortest possible length. Okay, so it's going to be in the middle here and go up. So the shortest possible length is going to be if that is perpendicular to the ground. Now, this is particularly easy because the formula for this is in the formula book. Okay, and it's this section here that I've copied out, the perpendicular distance of a point from a plane. So all we've got to do is have a look at our diagram. So scrolling up and down. My point is in the middle here. So if I call that X, so that's halfway along the 3 meters, halfway back, and 0 up. So that's where it is. Oh no, I've just used the wrong number because it's not 0.4, it's 1.2 back. So that's 0.6. Okay, so remembering that, okay, the coordinates of x were 1.5, 0.60. My plane, well, I can easily convert that to Cartesian. You just replace r with x, y, z. And then you can go straight to the fact that that's 7y minus 12z. I can move that over so it's in the right form. And then I can just substitute all those numbers into the formula. Okay, show a few more decimal places, then have a look and see what they wanted. They wanted the nearest millimetre, and mine's in metres. So to get the nearest millimetres, I'll have to go 0.993 metres. Then we've just got to state a limitation to the fact the boards are going to be modeled as planes. So they've got these boards around our shelter here. Well, planes don't have thickness. Boards will have thickness, which would affect the model. Other sensible things they were talking about, so you need to take into account the fact they're actually thick. They also said they might bow, so they wouldn't form planes. So we've modelled them perfectly straight, but that might happen, particularly over time with the weather.